This is Mathematical Fun by professors Alfredo Galvez Jr. and Maricela Leja Alvarez. Tonheim Lam, which means math is great, fun, mathematical fun, yes. Anyway, we're going to do with money in a little bit. Just show you some cash here. Pennies and dollars and stuff like that. Anyway, let's go. Let's start it. Okay, what we're going to do is, let me get the money out of here. There we go. Now the cash is all gone. Yes, okay. So now, mathematical fun. What are we going to do? We're going to do fundamental lemmas of linear, quadratic, and elementary first order differential equations. That's what we're going to do. Okay? So I'm going to start off with fundamental lemmas, like little theorems, I guess, of linear, quadratic, and elementary first order differential equation. So now, let's go from here. So now what we're going to do is, alright, so mathematical fun, fundamental lemmas of linear, quadratic, and elementary first order differential equations by professors Alfredo Galvez and Maricela Leja Alvarez, Tonheim Lam, which means great, math is great. Alright, so now, lemma of linear equation for ax plus b equals c, a is not equal to 0, b and c are real numbers, then x equals c minus b over a. So now I'm going to show you that this is the answer always for this problem. So ax plus b equals c, subtract b from both sides, so ax equals c minus b. So we have ax equals c minus b, divide by a, so x is c minus b over a. So now from there, that's the answer always. Put it back in the original problem, ax, but instead of x, put this in there. C minus b over a. A's cancel, so you have c minus b plus b. C equals c. Yes, it works. Good. So this is the solution for ax plus b equals c always, and under these conditions. Hey, looking for money and work? Get some money like that cash we showed you earlier? Yes, great food, great work, great boss. Open 24 hours. Mount Margie's. Go down there if you want to. So now, lemma of linear equations. There's the one we just did. So here's a problem, 2x plus 1 equals 9, a, b, and c, there they are. Put them in the formula. Put the letters in there, c and a b, and then work it out, and you're going to get 9 minus 1 is divided by 2, a divided by 2 is 4. Is that the answer? Let's check it. Put it back in there. 2 times 4, does that work? 2 times 4 is 8 plus 1. Is that going to give you 9? I say yes, it does. Yep, it's good. So it works. Now, that's using the formula for this linear equation. Now, suppose we say don't use the formula. So we have solved without the formula. So 2x plus 1 equals 9. So what I'm going to do is subtract 1, 2x equals 8. Divide by 2 is x equals 4 again. So 2x plus 1, put it in there. 2 times 4 is 8 plus 1. Is that going to give you 9? Yes. So you can do it this way, without formula or with the formula. Now, let's go to the next one. Lemma of quadratic equations, ax squared plus bx plus c equals 0. Now, what I'm going to do is I'm going to get the quadratic formula from this, but the way we're going to do this is we're going to complete the square on this, okay? And complete the square means we're going to first divide a all the way across. So x squared plus b over a plus c over a equals that. Now we're going to subtract ca from both sides. So this can be x squared plus ba over x equals c minus c over a. So now, we're going to go add this magic 1/2 of b a over a squared, 1/2 of b over a squared. This complete the square, that's what we're doing. So that's what we're going to do, add to both sides. It's the magic part. So now, what happens when we do this? I'll show you. So b over 2a, b over 2a. Multiply this out, this can be b squared over 4a squared, b squared over 4a squared. Now, what I'm going to do is get an LCD for this one, which is going to be 4a squared. Multiply this one by 4a. So we have minus 4ac over 4a squared, b squared over 4a squared. Now we can put these together as one big fraction. See it? From there to there. Now, next step, what's going to happen is we have this right here. And what we're going to do is we're going to factor this one out. Okay, now this one, there it is. And you can rewrite it if you want to put this first. This one's first, this one's last. But now, this one here, this is x plus b over 2a, x plus b over 2a, because b over 2a times b over 2a is b squared 4a squared, and if you get x on z, you get x squared, and you get this one, and this one's going to be 2b over 2a, becomes this right here. So this factored from there. Now, once you get that part, we have x plus 2a over 2a, x plus b over 2a squared equals this. Now, take the square root of both sides, plus or minus, plus or minus. So x plus b over 2a is left over equals plus or minus this. Now, I'm going to subtract b over 2a on both sides. So now we have x by itself. We're not done yet. It's equals negative b over 2a is this. Now, let's break this up into two square roots. This one, square root of the top, square root of the bottom, numerator, denominator. So this can be square root of b squared minus 4ac over square root of 4a squared, which is just 2a. Now, 2a, hey, they're matching. Now we can add these guys together. And guess what? We have x equals negative b plus or minus b squared minus 4ac over 2a, the quadratic formula. So x squared plus bx plus c equals 0. A is not equal to 0. Always the answer is going to be this. Always you can use this to solve it. So now let's use this formula. Okay? So lemma, a quadratic equation, there it is. This one will give you this answer. So now, at 1x squared plus 14x plus 24. This a, 1, b is 14, c is that. Put the numbers in the quadratic formula. There they are. Now, negative of 14 is negative 14. 14 times 14 right here. Negative 4 times 1 times 24 over here. Now, what's going to happen, we're going to start calculating all this stuff, arithmetic stuff. So we're going to get 196 minus 6, which is 100. The square root of 100 is 10. So we have negative 14 plus or minus 10 over 2. And we can break that up in two pieces right here. This is going to be negative 7 plus or minus 5. So that's going to be negative 7 plus 5, negative 7 minus 5, which is going to give me the answer of a negative 2 and a negative 12. This is using the quadratic formula. Now, can we do this another way? Sure, we can do without the formula. It's possible to factor this one, yes. So 24 times 1, 12 times 2, 6 times 4, 3 times 8, that's all that right there. Now, what's going to happen? We're going to do the 12 and 2. Because 2 times 12 is 24, 12 and 2 is 14. Yep. So x plus 2 equals 0, or x plus 12 equals 0. So minus 2 minus 2, x equals negative 2, or x equals a negative 12. Exactly the same answer we got using the quadratic formula. Now, so we did the linear equation formula. We did the quadratic formula. Now we're going to do a little bit harder. Differential differential equation. We're going to solve the first order linear differential equation where k is not equal to 0 and b is a real number. So now what does all this mean? Let's figure it out here. So y prime equals this, k yt plus b. That means that the solution is always going to be y of t equals c e to the kt minus b over k. There's a problem, there's the answer. Now, is that work all the time? Let's find out. Let's get the proof here. If you have the answer right here, y prime equals k yt b, first order linear differential equation right there. So now what I'm going to do is divide both sides by kyt plus b, both sides divided by, so these are gone, so that's a 1. We have y prime t over kyt plus b. Okay, and if you want to get some money, great boss, great food, get work, 24 hours, my margin is always open, always open. But anyway, let's go back to this first order linear differential equation lemma. So now, we're here, so what I'm going to do is now, I'm going to rewrite this y prime t as dy dt right there from your calculus class. Remember that old calculus stuff you did? There it is. So dy dt over this, and this is rewrite this over 1. So now we have two fractions. One's on top, one's on the bottom. So we're going to get the reciprocal, this number times the reciprocal of this, dy dt times 1 over kyt plus b equals 1. Reciprocal right there. Remember that from college algebra? Now we have dy, we have 1 dy, kyt plus b dt. Now, what I'm going to do is, on the next step, okay, on the next step, multiply both sides by dt. So now, when we multiply both sides by dt, what's going to happen is, this is gone, so we have 1 over kyt plus b dy equals 1 dt. Now, from calculus, we're going to take the integral of the left side, integral of the right side. So the integral of this side, integral of this side. Now, you notice that, what's the derivative? The derivative of this is not up there. This one's easy, just a constant, so we can integrate that. Now, how are we going to do this? Let's fix it. Okay, and then fixing it, what I'm going to do is, let's do it here. I'm going to put y prime of t, kyt b plus b equals this. Now, the derivative of this is going to be, we need the ky prime up there. So I'm going to put a magic k over k, which is a 1. See the 1 right here? Multiply both sides. This is by 1. So now k over k, same thing. And then 1 over k times k, I broke it up. So now I'm going to bring this k inside. It's a constant, so you can put it inside the integral from calculus, of course. So now k y prime of t and k y of t plus b. Now the derivative of this is a constant 0, and that'll be that. Now, once it's set up there, again from calculus, you can see that the integral f prime of x over f of x equals the log of f of x plus c, some constant. So we can do that with this because it's set up, plus the 1k is outside. Go from there. Let's go from there. So now we have 1k times the log of this plus c1 equals t plus c2. Two different constants, doesn't matter, they're just constants. Now I'll multiply both sides by k, k times this one, and k times that one. So now what's going to happen? This k over k, and this k times this c1 right here, kc1, and then this way distributed out. So now k over k is 1, don't worry about that, that's a 1. And we still have this. Now what I'm going to do is, I have ln of this plus this. Now I'll subtract this. The log absolute value of kyt plus b plus kc1 minus kc1 equals kt plus kc2 minus c2. Constant 1, constant 2 right there. Now what we're going to do is, next step, magic of course, we're going to say that ln of this equals this. Now I'm going to call this right here, these two guys right here, constant 1, constant 2. I'm going to put them together and call it constant number 3. Okay, this is a constant, that's all they are. So let C3 equal Kc2 minus Kc1. New constant, okay? Just substitute this in here, C3, see it? C3 for that. Now we have this. Now take e to the power of this and e to the power. E to the ln of this, e to that. Now e to the kt plus C3, well, we know that that's going to be e to the kt times e to the C3. In other words, add the powers, you get back to this one. This is from college algebra, of course. Okay, now we can write this as a product. Now we have another trick, of course, more magic. So we're going to do this. Let C4 equal e to the C3. That's a constant right there also. So a new constant. C4 equals e to the C3. So now e to this power and e to this power times C4, because this became C4. Now e to the log of that, what's going to happen there? You know what's going to happen in the next step. So e to the log of this is going to be that right there. ln of kyt plus b, e to the log is that. From college algebra formula, e to the ln of x is x. C4 times that. Just flip this around. Now we have this. So we're going to subtract b from both sides. Minus b minus b. So now we have kyt equals C4 e to kt minus b. Now divide both sides by k, and all the way across. So this is gone, this is still there, this is still there. So we have yt equals C4k e to kt minus b over k. Now, what are we going to do here? We're going to go ahead and call it a new constant, of course. Big C. The big giant C is going to be C4 over k. Okay, maybe go back again. So C4 over k, this one right here is going to become the big C. So we're going to replace it right here with this. So yt equals C e to the kt minus b over k. Now the answer. So if you start out with y prime of t equals kyt of this, guess what? This is the answer always. This is the original problem. There it is. First order linear differential equation. So now we know how to do it. So now first order linear differential equation. There it is. Y prime t. Let's check it. So there it is, the problem. Y prime is going to be c to kt times derivative of this, and this is a constant 0. Don't worry about it. So we have c to kt times k, or ck e to the k. Now, I'm going to substitute this back in the problem. See if this works. Now check it. Ready? So we have yt is this, y prime is that. So there's a problem. Put the numbers in there. Ck e of t for this equals k times this side. Well, that's going to be kc e to kt minus, and this k cancels right here. So we have b minus b, goes away. So we ended up with ck e to kt, kc e to kt. Just flip this around, and you're going to have CK e to the KT equals exactly CK e to T. Good, it checks. It does work, always. So now we know. So let's apply it to something with numbers and money, huh? So to go to a private university, 1 year you only need $60,000 for tuition. So you borrow $60,000 interest rate of 6% per year and agree to make monthly payments of $600. Solve the first order linear differential equation with initial condition y of 0 is 60,000. So here it is. Divide it. I got 0.005. Put the numbers in for the letters. See the K, see the B. So now we're going to have y of t equals this. Substituting these numbers in here using the formula we just developed that lemma. So we have c e to that number minus negative over the positive. So this right here is going to be a positive 600 over this. Now we're going to go ahead and work it out. We have c e to that plus 120,000. Inertial condition y 0 is this. So put a 0 there, put a 0 there, work it out. And e to the 0 is 1. Okay, see this is 1, e to the 0 is 1. 1 times that, see? And we have this, subtract, subtract. So guess what? C equals negative 60,000. So now the answer is y of t equals negative 60,000, e to the 0.005 plus 120,000. Let's use this. We know how to do it. So now let's find out. After you make one monthly payment, 0 payments, you owe the money. 1 month, you owe 59,699, 59,396. 2 months, 3 months, you owe money. Keep going, keep going. Okay. 4 months go by, 5 months go by, 6 months go by. 1 year later, you still owe 56,289.80721. And let's keep going. 2 years later, you owe 52,350. 3 years later, you owe 48. 5 years later, 39. 7 years later, you only owe 28. That's not bad. Half done, man. You're half done with that $60,000 loan. So now we have 120, 10 years. We have 11.42 years, 11.5 years. Yes, 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 yes. 138 months later, or 11.5 years later, you're done. That $60,000 with the little finance charges comes out to $82,800. Not bad, huh? So you paid $82,800 for that $60,000 loan at 6%, a good interest rate. Now, okay, let's say you bought $60,000 interest rate of 12%. Uh-oh, not as good, but take it anyway. Your payments are going to be a little higher, $617.17 per month. Solve the first order linear differential equation with initial condition, y0 equals this. So now, y of t is this. Again, we're going to put the numbers in there in our formula. We just did it, remember the lemma. So put the numbers in there, negative, negative, positive. So we have this. And we're going to put in our initial condition. So y0 is this, so put as y0, which is going to be c to 0, 1. 1 times that c plus this. Subtract, subtract. So c equals negative 1717. There's our formula right there. Now we're going to use it to calculate. So 0 months, you owe 60,000. That's okay. 1 month goes by. 1 year later, 12 months. 5 years later. 10 years later. 17.5 years later. Because remember, this is a higher interest rate. It takes a little bit longer. And you're half done. 25 years, you are half done. 27,000, half of 60, I guess, close. And 30 years later, you only owe $122,000. No, $122. Hey, that's nothing. Nothing money. So for $60,000, you ended up paying $220,946.86. So this times this, $220,946.86. It's not bad, 12%. Draw the graph. So the graph, the loan, and as you make payments on it, it goes lower, lower, lower. To find E358, you are done. $122. That's it. Only 30 years later, and your payments are going from your bank account to the bank, to the credit, to pay the loan. So, 30 years later, you paid $220,946.86 for that $60,000 loan. Okay, not bad, not bad. Let's make a little number. Let's say $1,000. You bought $1,000 your credit card interest rate of 24% per year and agreed to make monthly payments of $20.01. Super easy money. Because you're going to go spring break with your 4 best friends. You got there on the beach, condominiums and all that fun, surfing and stuff. So now, Mustang Island, I guess. Solve the first order linear differential equation with initial condition, y0 1,000. Put the numbers in just like we did using that formula. So we put these numbers in here. We notice that we have this. And there we go. Now the initial condition is y0 is 1,000. Let's use it. Put it in there. You're going to get 1,000. So from there, we have this condition right here. And e to 0, 1 again. C plus that. Subtract, subtract. C equals negative 0.50. Now, put it in the formula. And there it is. So we have y0. There's a formula. y0, you owe 1,000. So you put in your credit card to go to Mustang Island and have fun with your friends. 4 best friends. 1 month later, 2 months later, 3 months later, 4, 5 months later. 1 year later, you still owe 999.86 of the vacation. That's okay. 5 years later, you owe 998. That's not bad. 10 years, you owe 994. 20 years after your vacation from Mustang Island, you still owe 939. And 25 years later, you only owe 798. That's not bad. That's not bad at all. It's pretty good. 28.83 years later, you're half done. What? What? That's not... Can't be right, can it? Can it be right? Let me see. Holy cow. So, 1 month, 2 months, 3 months, 4 months, yes. 1 year later, 5 years later, 10 years later, 20 years later, 25 years later. So we ended up paying what? 1,000 cost us 7,603. Holy cow. Or, here's a graph. That's what happens. 1,000 really cost us 7,603. That's not bad. So, you borrowed $60,000 on your credit card. Interest rate 24%. Agree to make monthly payments of this. Go to Hawaii vacation with 4 best friends. What's going to happen? Solve the first order linear differential equation. Put the numbers in. You got it right there. So we have y0 equals this. So now the initial condition is y0 60,000. So now let's go from there using the formula again, of course. So put it in there. E is 0 is 1. We end up with C equals negative 30. So here's our formula. Put the number in y0, 60,000 is what you bought to go to Hawaii vacation with your 4 best friends from college or wherever. So now what happens? 1 month goes by, 2 months, 3 months, 4 months, 5 months later, you still owe 59,996. 1 year later, you still owe money. A lot, a lot. 10 years, you owe 59,699 from the 60,000. 20 years later, you owe 56,384. 25 years later, you're 47,927. Half done. 28.83 years. You owe 29,000. That's not bad. 30 years go by. 31.67. You're done. Yeah, you only owe 84 bucks. But you gave them for that $60,000 credit card to Hawaii for your 4 best friends, North Shore, wherever you went, $456,228. That's it. At 24%, of course. Hawaii was great, though. Don't worry about it. Draw a picture. You get 60,000, you pay it off, and 380, it's over. But you gave them 456,228 for this $60,000 loan on your credit card. That's not bad, because I'm gonna tell you right now, internet has all the cool pictures of you and your friends out there. It's great. And the surfboard, I mean, it's awesome. The one broke, but that's okay. Your Hawaiian stuff on there, had a great time out there. And the math monster, oh, credit card monster. That's really what's scary. Not math monster, but getting credit and using it and having to pay back all that interest, that's a credit card monster. And holy cow, no, not more scary than the credit card monster. How about these guys? Still not more scary than the credit card monster. I'll tell you right now, no way. 1, 2, 3, 4, 5, 6, 7, 7, 7. There they are, 7, 7. What's more scary than this? How about this? How about Crunchy, the giant one? Is that more scary? No, 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 no. Credit card monster, credit card bugs are more scary than anything else, because credit card monsters and are more scary. I'm just going to tell you that right now. So hopefully you learned something about credit cards and stuff and differential equations. Good luck in your calculus classes, differential equations, differential equations, whatever. Theory of calculus, whatever you take. Good luck to this Professor Alfredo G. Oliveira Jr. Bye.